This video is brought to you by mywayteaching.com.
In this part, we are discussing about the limiting process. Okay, by saying this because you can easily understand that limiting process. So you can see in these figures, that is from A to D. In these figures, the thick line represents the path of an object. Okay, the thick line, you can see the line which is in blue color, it represents the path of an object. So which is at P at the time T, and it will be at P1, P2 and P3 represent the different positions of the object after the time intervals, like at delta t1, delta t2 and delta t3 respectively. Okay, and you can see delta r1, delta r2 and delta r3 in this figure. You can see, isn't it? Delta r1, delta R2 and delta R3 are the displacements of the object in times delta T1, delta T2 and delta T3 respectively. See, the direction of average velocity, that is V bar, is shown in figures A, B, C and D, which means the direction of the average velocity in these four figures. Okay, for three decreasing values of delta t, that is delta t1, delta t2, delta t3. So delta t1 is greater than delta t2 and delta t2 is greater than delta t3. Okay, as delta t tends to 0, delta r also tends to 0, and that you can see in the fourth figure. Okay, and its direction is along the tangent of the path, as you can see in this particular figure. Okay, as delta t tends to 0, delta r also tends to 0. So as the time interval delta t approaches 0, the average velocity approaches the velocity v. The direction of v is parallel to the line, that is tangent to the path. Okay, so first delta 1, and slowly we are decreasing the values of delta. Okay, then we'll consider delta 2, t2, and then delta 3. We are again reducing the value of delta t, and again we'll delta t approaches 0 in the fourth figure, and then we'll get the direction of the average velocity. It becomes equal to the velocity v, and it is the direction of v is tangent to the path, isn't it? So this is the velocity. And now let us consider some mathematical expressions for this. So I told you the direction of velocity at any point on the path of an object is tangential to the path at that point, and it is in the direction of motion. So the velocity v can be represented as dr by dt, isn't it? The displacement time interval. Okay, and this can be represented as limit of, as delta t tends to 0, dr by dt can be represented as delta x by delta t into I cap, isn't it? The position vector delta r, that is delta y by delta t into j cap. And if you take out this I cap outside, we'll be remaining with limit of delta t tends to 0, delta x by delta t plus j cap limit of delta y by delta t, isn't it? Or we can represent v as I cap dx by dt plus j cap dy by dt. That is given by Vx into I cap plus Vy into J cap. So Vx is nothing but the dx by dt and Vy is nothing but dy by dt, isn't it? So this is the velocity v. So if the expressions for the coordinates x and y are known as functions of time, we can use these equations to find Vx and Vy. So the magnitude of velocity v we can get by using the components Vx square and Vi square. Similarly, we can get the direction by Vy by Vx. So the direction V is given by the angle theta, and that theta is nothing but tan inverse of Vy by Vx. Is that okay? So Vx, Vy and angle theta are the important parameters to find the magnitude as well as direction. So you can see in this particular figure the components Vx and Vy of velocity v and the angle theta it makes with the x-axis. Okay, you can see in this figure, and Vx we can, by using simple trigonometry, we can write it as v cos theta, and Vy we can write it as v sin theta, isn't it? So you can see in this figure. So this is about the velocity concept. So now let us study about acceleration. Okay. The average acceleration a of an object for a time interval delta t moving in xy plane is the change in velocity divided by the time interval. So average acceleration of an object is given by change in velocity divided by time interval t, okay, delta t. And this velocity, just now we derived the equation in the form of using its components Vx and Vy, that is given by Vx into I cap plus Vy into J cap. And the time delta t. And you can simplify this by taking Vx delta Vx by delta t into I cap plus delta Vy by delta t into J cap. Okay, this is the average acceleration. So in simple terms, we can write average acceleration as ax into I cap plus ay into j cap, isn't it? So where Ax is given by delta Vx by delta t, and Ay is given by delta Vy by delta t, isn't it? So the average acceleration of an object for a time interval delta t moving in xy plane is nothing but the change in velocity divided by the time interval, that is delta v by delta t. Then what about acceleration? Now we saw what is average acceleration. The instantaneous acceleration is the limiting value of the average acceleration as the time interval approaches zero. So the instantaneous acceleration is nothing but the limiting value of the average acceleration as the time, that is delta t, approaches zero. Okay. Since delta v is given by delta Vx into I cap plus delta Vy into J cap, we have average acceleration A by time interval delta t. The limiting value of this gives the acceleration, that is instantaneous acceleration. So I can be, this acceleration A is I cap limit as delta t tends to 0, delta Vx by delta t plus J cap limit as delta t tends to 0, delta Vy by delta t. Okay. So in other words, we can write it as A is equal to Ax into I cap plus Ay into J cap. So where this Ax is nothing but dVx by dt and Ay is dVy by dt. So, as in case of velocity, we can understand graphically the limiting process used in defining acceleration on a graph showing the path of an object's motion, isn't it? In order to understand this limiting process, we'll consider graphs. So, let us see those graphs. So you can see in this figure, the P represents the position of the object at the time t. Okay. So the P, so the P represents the position of the object at the time t. And P1, P2, P3, you can see here P1 here, P2 here, P3. So these represents the positions after time intervals delta t1, delta t2 and delta 3 respectively. And we are considering the decreasing time intervals, that is delta t1, delta is greater than delta t2 and delta t2 is greater than delta t3. The velocity vectors at points p, p1, p2, p3 are also shown in the figure. See the velocity vector v, you can see here. So at points p as well as at points p1, p2, p3, you can see in this diagram the velocity vector at point p1, P2 and P3 is also shown in this figure. So in this case of delta t, delta v is obtained using the triangle law of vector addition. So by definition, the direction of average acceleration is the same as that of the it is same as that of the velocity, that is delta v. So as delta t decreases, the direction of delta v changes, and consequently the direction of the acceleration also changes, because the direction of delta v and the direction of acceleration both are same. So finally, as delta t approaches 0, okay, the average acceleration becomes the instantaneous acceleration, and it has the direction as you can see in this figure. So as delta t becomes 0, the average acceleration becomes instantaneous acceleration, and its direction is given like this. Okay. S- in all these three cases, you can see the velocity and acceleration directions are same. So, in one dimension, the velocity and acceleration of an object are always along the same straight line, either in the same direction or in the opposite direction. However, for motion in two or three dimensions, velocity and acceleration vectors may have any angle between 0 degree and 180 degree between them. Okay.